We're going to move on to Sibu Martlo's question. Sibu, thank you for this. It's a financial maths question. I'm going to try and do it as quick as what I can with you. It says question 6.1. Now, folks, I'll read, and as I read, I'll put the information that's necessary on the screen. The total number of marks for this question is 15. It shouldn't take you longer than 12 minutes to do. It's not a difficult question. Let's read. Calculate how many years it will take for the value of a truck to decrease by 50%. Now, for something to decrease by 50%, folks, we can immediately write the future value is, or the present value of the truck is, the future value is half, of the present value of that truck. Okay, then of its original value, it says if depreciation, so the rate, and I always with depreciation, I just put an R with an arrow downwards to remind myself it's depreciating. The depreciation rate is calculated at 15% per annum on the reducing balance scale, so that means it's compounded annually. It's a compound interest problem. Okay, so folks, let's have a look at what do we do here. The future value on the left-hand side can be replaced by half the present value. Okay, so usually we would start off and we would say, oh, okay, the future value is the present value, 1 plus I to the n. Now remember, this I is in this case the value of R divided by 100, which is 0.15. So if I replace the left-hand side with a half of PV, you can see that the PV actually does not matter. I can just remove them because they're common on both sides, and on both sides I have factors that I am considering. Okay, so let's see. This becomes 1.15 to the power, it's depreciating, this is a negative. Okay, if it's depreciating, this is a negative. So I've got 1 minus that, which is indeed 0.85 to the power of n. Now, we said we can just ignore that. So what am I left with here? I'm left with 0.85 to the power of n, which is equal to a half, which is 0.5. Those two bases, there's just no ways that you're going to do something to 0.85 and 0.5 to get them to look the same. So you have to run to logarithms to solve this problem. Okay, so we're going to say immediately that n is the log of 0.5 divided by the log of 0.85. Now, some of you might have fancy calculators, so you can say the log base 0.85 of 0.5. Now, I've done that calculation for us. I haven't done it. Let's quickly do it. The log of 0.5, where's my calculator? There we go. So the log of 0.5 divided by the log of 0.85. And what's interesting here is it's 4.265. Okay, so my result for this one is 4.265, and there's a few more decimals. So in the middle, it will take 4 years, and that part of a year for this to halve. But let's say we only compound this interest once a year, so it will take us 5 years before this one, for this truck to lose 50% of its values. So this n is 4 years, and it comes out 2.2 is about three and something months into the year. It will have lost 50% of its value. So because we only compound once a year, it will lose that value over a period of 5 years. Don't round down to 4. That's the key thing here. Okay, let's look at the second part of the question. It says, every month Tenfold deposits 1,500 Rand into a retirement fund that paid interest. So, okay, let's make notes. There's a regular payment. That regular payment is 1,500 Rand, and they said to us it is per month into an account that pays interest at 9.2% per annum, compounded monthly. So we're sitting with compound interest, number one, and number two, we're sitting with a nominal monthly rate, which we have to turn into an effective monthly rate. Let's do that while we see this, on our screen. The I value for this will be 9.2, which I have to divide by 1,200. And if I divide that by 1,200, I get 0.0076, and the sixes recur, folks. So that I am ready to use. I like doing this in financial maths, getting rid of the ugly fractions so that I do not trip over the fraction. Most of your mistakes in financial maths comes with your calculator, where you have fractions, you forget about brackets. We do simple things. So let's try and simplify it right from the beginning. Okay, then it says, Tsepo made the first installment on his 23rd birthday. So on his 23rd birthday, he made the first installment. He carried on paying. The last installment happened 1 month before his 55th birthday. Okay, now folks, if we work that out, remember, it's like sequences and series. It's 55 minus 23 plus that 1. That's the number of years that this annuity was running. From his 55th year, or from his 23rd year to his 55th year, that leaves us or gives us a total of 33 years. It took him to run with this annuity. Now remember, it stopped 1 month before his 55th birthday. It started on his 23rd birthday. So if it's a timeline, it started at T0, and here 33 years multiplied by 12 will take us to months, and that gives me 396 months. Okay, so this annuity ran for 396 months up to his 396. That would be up to his birthday. Okay, now remember, he made his last payment a month before his 55th birthday. This is his big birthday. Okay, so here we have 396 payments. Remember, because you started at 0, and right at the end, the annuity terminates over here. Right over here, you need to take it 1 month forward, because let's just see what they ask. How much money did he have in this account on his 55th birthday? Very important. Not a month before his 55th, on his 55th. Okay, so let us structure this question and see how it works. It's always useful to use a timeline. Our monthly payments is 1,500. Okay, so this is a future value of an annuity. We run to our future value formula. It's 1,500 and then 1,0076. Now remember, folks, it recurs, so you fill your screen with sixes. Don't just write in 1,0076. 66666 until your screen is full of sixes. There are 396 of those payments inside this annuity, minus 1, divided by 0.0076 recurring, and that has to go forward for 1 month to get to the big day when Tsepo turns 55. Okay, he started immediately. He made the final payment the month before his 55th birthday. So because we started at timeline 0, it is 396 payments that lies inside the annuity. Remember, for future value problems, the moment you stop paying, the annuity terminates and you go forward. Normal compound interest, by the way. Okay, so if you go to your calculator and you work this out, this gives you 3831,277,93. Now that I still need to take forward. So this is just the sum over here. 1,0076 recurring. So let's calculate that here with our calculator. Let's reset that. We have our, 3831,277.93 multiplied by 1.007, and now you'll see, put as many sixes as I can, and that gives me 2860651, or 3860651, 3860651, 3860651 is what Tsepo would have in this account on his 55th birthday. Remember, folks, he started paying on his 23rd and he stopped a month before the 55th. That makes up for a total of 396 payments here. And then, so the annuity terminates. It runs from there to there. 396 payments. It has to go forward 1 month to get him to his 55th birthday. Okay, let's look at the last part of this particular question. The question 3 says the following, and I'm going to read and, as usual, make notes. Has something there, has 150, the print is a bit bad. Abram has 150,000 to invest in 2 separate accounts. So the present value of the money that Abraham has is 150,000. One account pays interest, so we're going to say R1 for the one account, pays interest at a rate of 8.4% per annum, compounded quarterly. Brilliant. Nominal quarterly rate. We haven't seen one like that for ages. Okay, then they say, where am I now? And the other account pays a rate of 9.6. So the second rate is 9.6% per annum back to compounding monthly. So we have to fiddle with both of these because they're nominal rates. Then they ask us, how much money should he invest in each account so that he will collect the same amount from each account at the end of 12 years? Okay, so this is going to run for 12 years. So let's say in account 1, he's going to invest X rand. Okay, so PV1 will be X, and present value 2 will then be the remainder of the money, 150,000 rand minus the X that he has already invested. Okay, folks, big problem is per annum compounded quarterly, per annum compounded monthly. So we need to change our interest rate. So let's change this to I1. I1 will be 8.4 divided by 400 because it's quarterly, remember. So this is a beautiful 0.021. No recurring decimals, nothing. So that's quite a nice number to work with. 9.6 is the second one. So I2 is going to be 9,6 divided by 1,200. Remember, we divided by 12 to make it effective per month. Then it's still an R value. Then we have to divide by 100 to turn it into a decimal. Okay, so if you do that calculation, you also get a nice round number, 0,008. Okay, so they say the future values must be the same for both of these. So we can weigh it into the formula and make them equal. Let's see. Phase 2. On the left-hand side, we would have invested X at this particular rate, which is 1,021, and it's for a period of 12 years. Now remember, this is an effective quarterly. So there's 4 quarters in a year, so there's 48 quarters in 12 years. On the right-hand side, 150,000 minus X. We are investing at 1,008, and this is done per month, so the power will be 144. Now folks, this is simple calculator work from here onwards. I want to get to our geometry question, so I'm going to fast forward us over here. We get on the left-hand side, we're going to get 5,86170 with a few more decimals X, and then that is now, once we have taken this X and this part and we've brought them all to the left. On the right hand side we have 150,000 multiplied by that factor that we have over there, and that gives us a beautiful 472,506,604. So all we need to do to find X is divide this number by whatever's on the left-hand side. That gives us 80,609 Rand and 5 cents. Should be, remember, this was in account number 1. And in account number 2, he's got to use 150,000 minus this. So account number 2, he's going to invest, Abram is going to invest 63,390,95. Okay.